research, I don't think he needs much of an introduction. Thanks for joining us today, Ian. I'll let you take it from here.
Thanks, Georgia. So, yes, welcome. Thank you, and kia toto. I'm happy to be here. Today we're going to take a slight detour from some of the previous webinars, and we're going to have a little bit more an informal talk through, a bit less focus on the science, and I'm going to talk to you a little bit about diving in Antarctica. And I'll start by sharing my screen, and I'll get the right one. So diving for data, and I want to kind of talk about this really as enabling technology. And the top two pictures there in this slide, you can see a primus from Borchgrevink's expedition at the end of the 19th century. And in the same way that the primus and similar technologies enabled the exploration of the interior of Antarctica, then it's development of diving technologies which have allowed us to explore some of the edges of Antarctica. All right. Okay, so often people think, who was the first person to dive in Antarctica? And it seems to be a young fellow called Willie Heinrich back in 1902. And Willie was on Drygalski's German South Polar expedition. He was on the Gauss. And as now, the divers were highly esteemed in the hierarchy, and Willie was actually there as a second carpenter. And he was biffed over the side while the ship was stuck in ice, wearing something like the picture on the right-hand side. And his job was to recork parts of the ship which were starting to leak. So yeah, so Willie was probably the first person to dive in Antarctica using what was then called the standard diving dress. Science diving started sometime later. And if you want a really good history of diving under Antarctic ice, then there's a publication by Peter Brueggemann, from which I've shamelessly plagiarized one or two of the photographs you're going to see. So science diving started really about 1961 with the US program. Then, as now, they used dry suits, they had dry gloves, they dived out of heated huts through holes cut through the ice. And in some ways, apart from some details of the technology, then in general, the operation was pretty similar. The divers, of course, were the first to see the spectacular and actually kind of amazing underwater life in Antarctica. They made collections, they made first observations on animals that were growing on the bottom and associated with the ice underneath. In 1963, the UK also started that diving program at Sydney Island. Russians, it's around about 1966 at Mirny Station, and at this stage we were starting to get to developing more advanced approaches to science underwater, as was common across the globe at the time, not just in Antarctica. We were getting more and more sophisticated, and experiments were starting, manipulations were starting to be made, and in turn to understand not just what's there, but also how those systems were functioning. In 1985, I believe my research suggested was the first New Zealand dives out of Scott Base. And I just want to kind of mention briefly Steve Mercer, who was a real guru during the early days of New Zealand diving, who unfortunately died earlier this year. So yeah, thanks for all the help over the years, Steve. So my personal connection started in 1978 when I was working with the British Antarctic Survey on Sydney Island, and these are a couple of pictures which we've rescued from back then. So, and I just want to touch briefly on some of the equipment that we were using. You can see that at that time we were diving in wetsuits, and we were using what we call twin hose demand valve. And so this is a Mistral, is the little guy up in the top center there. I mean, you can see this is a breathing valve, which is kind of different to what you'd be used to these days. And the reason why we're using this gear, so wetsuits and twin hose valves, was because we knew it worked. And diving in Antarctica has always been a very conservative and an incredibly safe operation because of that conservatism. And we really focus in on things that we know are going to work in what can be a slightly difficult physical situation. So you can see that's me on the left-hand side. I was going down in our holes. Holes weren't so big as they in those days. So wetsuits, twin hose demand valves, and we used this gear for diving throughout the winter. Nowadays, things are a little bit different. This is one of our divers about to jump in a hole, and you can see dry suits are now de rigueur. The reason why we didn't use dry suits way back was because, first of all, we all trained in wetsuits. So science diving was all done in wetsuits. Wetsuits were then much more robust and much more reliable than the dry suits that were around. They had to last for a long time, and it's easier to effectively repair a wetsuit than it is to repair a dry suit. But modern dry suits are way warmer, and they are pretty much, well, everybody uses them now. You can see that the regulators change. We use 2 completely independent air supplies through first stage and second stage. If you look closely here, this is a setup after it's been in the water. You can see that the regulator on the left, the main one we were breathing through, is covered in ice. That's quite normal. That's simply just from the cooling of the air, the high pressure air as the pressure is reduced. And you can see here that, as I said earlier, we're really conservative. We know the gear that works, and these 2 makes of regulator are the 2 which really we find the most effective under particularly cold conditions. Yeah, so the ice film on the outside of regulators is fine. Our biggest problem in technological terms is ice film on the inside of regulators and inside of the second stage in particular. And here you can see a regulator where ice is formed inside, and that malfunctioned during a dive. The dive, of course, has to be terminated at that point. Okay, so dive equipment is not really greatly different to what you might use in cool water elsewhere. It's carefully chosen to be safe and reliable. So that's one technological challenge. The other technological challenge is actually getting through the ice into the water itself. And so making a hole is a tricky thing. And there are whole ways of technology, whole ways of doing it. This is the Italian approach, which I think is really super cool. So the Italians have built this device. It's a giant hole saw. If you look at it working through there, you can see essentially it's just going to drill a hole right through the ice. Once the hole's made, you can lower a rope through, you can drag it out, and you eventually end up with a nice core taken out of the ice and a nice hole left behind. So that's the Italian method. There are many other methods. When we're diving inland, so when we're diving in inland lakes in Antarctica, of which there are many, then we're constrained because everything that we use has to be flown in by helicopter. And so we make our holes in a slightly different way. We begin by drilling a hole with a small ice drill. That's definitely not going to be big enough to dive through. So we drill the hole and we pull that drill out, and then we insert a melter. So there's a copper coil down that hole, which is essentially being heated, and it's just going to sit there for 24 hours, and it's going to melt a nice big hole, which will be big enough for a dive to go through. So the hole making technology depends entirely on where you are. If you're on sea ice, you can drill. If you're on lake ice, then you have to come up with an alternative strategy. So enough on the technology now. So I was going to talk a little bit about some of the science that goes on. So initially, as I said earlier, then it was a whole new world to explore. There were whole new things to collect. As we become more familiar with what's there, then the questions that we ask are different. We're concerned about the physiology of organisms, and in particular for the Antarctic Science Platform, the way that the ecosystems are structured and function, and how those may be vulnerable to shifts in conditions as the climate changes over the next 100 years or so. So the types of questions that we've asked have changed. They've become slightly more complex, and to a large extent, our ability to do that reflects the fact that we're using newer equipment, which improves our dexterity, improves the length of dives we can make, and it also opens the whole concept of diving in Antarctica to everybody. You know, you don't need to be a superstar to dive in Antarctica. Anyone who's suitably trained and can do it. It's a kind of a well-kept secret that Antarctic diving is actually the easiest kind of diving you can do. You basically sit on the side of a hole and fall in, and come out when you get cold. So yeah, so it's opened it up to people with a whole range of skills, and the equipment has allowed us to do a whole lot more things. it's no surprise to anybody, I'm sure, who's watching here, the contrast between the spectacular nature of the biology underneath the ice and the incredible sparsity on land. And it never ceases to amaze when you do actually go through ice and you kind of turn on a torch and you have a look at what's around, and just how extraordinary it is that this is going on underneath this ice in this frigid environment. And because you're all familiar, I'm not going to focus really on that so much, but I want to kind of introduce you maybe more to some of the equally extraordinary, but in different ways, communities which are growing in inland waters in Antarctica. So these are images that are taken from under the ice of Antarctic lakes, in 3 different lakes here. And you can see that we are looking here at what we call a microbial landscape. So everything in these lakes is microbial. All of these structures are built from bacteria, and all of these structures are built by bacteria. And so this is an utterly unique environment, which is like nowhere else on this planet. And one reason why we're interested in these systems is because they really are changing, and we can see them changing, and they're changing due to the changes in the hydrology of our lake systems. This is a plot of lake level between 1945 to 2020, and you can see this is Lake Vanda, and it's increased in depth by around about 15 meters over that period. And it's increased in depth because more water is flowing in. And it's an unusual lake in that it occupies a closed basin, so water can flow in, it can't flow out. So the more water flows in, then the deeper and deeper the lake gets. And as these lakes get deeper, then environmental conditions change. And one thing we're particularly curious about are how these microbial ecosystems are able to accommodate those types of change. So I just want to show you a little video here. And here we're looking at a microbial community at a really important kind of biogeographic zone in Lake Frixell. And what you're looking at in the black on the left, and I'm just going to, I'll go back up. I'll just get up to about here, and I'm just going to pause it if I can. What you're looking at is on the left-hand side, black material, which is now growing in an anoxic environment. A few years ago, it was growing in a fully oxygenated, it was a photosynthetic microbial mat. But as the lake has got deeper, it's got darker too on the bottom. And so the community that was able to photosynthesize, it got enough light to photosynthesize, it's now being overcome by organisms which don't photosynthesize. The blackness is manganese precipitating, and on the right hand side you can see the photosynthetic material which is slowly retreating up. So we're particularly curious in these aquatic systems as to how they're going to respond as the whole hydrology of Antarctica starts to change, as things start to warm up. And the answer is it's complicated, right? Rising lake levels creates new habitat, but it also changes the habitat under which things that we think of as iconic Antarctic ecosystems are growing. So we're seeing change. We're not always seeing complete losses of systems. And in this picture here is from Lake Vanda, where what we're seeing is, despite this rapid lake level rise, then the communities are able to keep pace. In contrast, some other situations, this is a picture from Lake Joyce, where we have this very narrow band of what we call stromatolites, which are microbial carbonates precipitating communities, which only occur in a very narrow band in this valley, and they have to be photosynthetic to survive. And now these communities are no longer photosynthetic. So this is the type of situation in which we are losing some of these really iconic Antarctic communities in these lakes because of the dynamic way the habitat's changing and the physiological constraints that these organisms live under. Okay, so I don't have time in this talk really to delve in detail into the science that we do, and what I want to do instead is kind of look a little bit more into the future and think how things might change as technology continues to evolve. And so one issue is the extent to which some of the things that we use people to do now can actually be replaced by machines. Okay, and so one of the, I'm going to show you a bit of a video here. And I'll turn it down a tiny tad. So a couple of points here really is just the footprint of the dive operation. This whole picture you can see here, this whole setup is only as it's a dive camp, and it's just for the diving. You can see the equipment that we need is huge. We need a lot of people, all the stuff that's got to be flown in, and so what we are seeing here is just the logistic footprint of a dive operation. Many people, lots of gear, and sometimes people ask, changing the subject a little, sometimes people ask, what's it like to go through a hole in the ice? Well, that's kind of what it's like. It's incredibly, actually, it's a really relaxing feeling, because all that gear you've got on, all the hassles you've got before, all the expectation. Once you've gone through that tube, if between the surface and the under ice conditions, then you have a chance to completely relax and just get on with your job. So going through a hole in the ice is a pleasurable thing to do for most people who've done it more than once. Okay, so to keep it on this issue about technology and constraints on divers, then in this picture, what we're doing is we're measuring photosynthesis of these microbial mats growing on the bottom of one of these lake systems. And on the right-hand side, we have on the right-hand side, you can see a cross-section through one of these mats, and you can see we have these annual laminations, which are photosynthetic growth. Every year we get one more layer, and they're a millimetre or so thick. And what we're doing is measuring the rates of photosynthesis within those layers. To do that, we have to lie completely still on the bottom of the lake, and we need to move these probes up and down by fractions of a millimetre. And you can only do that for so long before you start to get too cold and you start to shiver too much, and you can't make those kind of fine, detailed observations. So technology comes to our aid here. This machine you can see on the right, it's a machine which we can deploy from the surface. It sits on the bottom, it makes those measurements for us, and it can sit down there for as long as you want, really. This you can see here is the plot on the left are some measurements of oxygen concentration and photosynthesis that this machine took over a 24-hour period, which of course is completely impossible for a diver to do. So more and more we are looking for ways in which we can reduce the constraints, the problems with the diver constraints, and come up with technology which can help us move around that. And there are other tasks that can be robotized too. So this is going back to the ocean for a bit. This is looking at kind of a standard sampling technique. It's become known as a technique developed by Vonda Cummings and Drew Laura at NIWA. And it's becoming a standard Antarctic technique. So we put out these tapes, we mark areas where we're going to take core samples from, and then we have detailed video imagery of these transects. We can come back to them time after time, and we can look at change, we look at the dynamics, and we look at population demographics through these types of analysis. And so what we are, there's elements of this which take up a lot of time. Again, you can see we've got divers in the water. These divers, they've done their dive, they're sitting around waiting to come up. They have to do their safety stops. Everything is complex, time consuming, and the whole system only reverts to its natural pristine state once we're all out of the water. So we have high footprint, and potentially in some locations we're impacting on the environment. So we're moving, this is the picture on the left is something you'll see more and more in Antarctica. You see people in the most spectacular scenery in the world watching telly. And what they're watching here is pictures from an ROV, which is a remotely operated vehicle, which is shot down through the ice. And I'll just show you this little bit of footage from this ROV. So here we are, we're going down through the ice in the same way that a diver will. And once we get down through the ice, then in the same way the diver will see the whole world start to get dark. We'll be looking up and we'll be seeing the sea ice, but it's obviously a camera on an ROV does just a good job of videoing a transect as a camera being held by a diver. It can do it for longer and it can do it for deeper. Sometimes also though, we get these real insights from this technology that we wouldn't otherwise get. So if rather than put the camera on the bottom of the ROV, you put it on the top, And I'm just going to pause here and go back a second because I just want to explain that here we're looking up at the ice from underneath with the camera sitting on top of an ROV, and we see these structures which are utterly weird. We see the coloration here is due to algae which are growing on the bottom of the ice. These mounds are mounds of ice crystals, and the little white dots you'll see in the top there are also things which are features which you don't really kind of understand until you see them a little closer. So we move the ROV in a little closer, and you can see that these little bright dots are actually little inverted icicles. We call them brine icicles or bicycles sometimes. And you can see that they are channels in which brine, so that's really cold, really highly salty water. Sorry, I'm going to go back up. And I'll go to the end of that again. Really salty water. These are channels where that salt water is funneled down through amongst these ice crystals, and because it's really salty, it can be really cold, and ice forms on the outside of the channel, so you get these hollow brine icicles forming underneath. And looking at that picture too, you can see that these brine icicles are occurring in this really complicated crystalline matrix. And one of the really cool things that we're looking at in the Antarctic Science Platform now is to try and understand the significance of these ice crystal matrices for ecosystem purpose functions. It's a really difficult environment to look at because it is so delicate, fragile, but it's full of all sorts of creatures. So we know there's a whole ecosystem going inside, and not least, it seems to be the kind of the initial breeding area of this little fish guy here in the middle, who is an Antarctic silverfish. Antarctic silverfish are the commonest pelagic fish in the Ross Sea sector. They are a key link in all of the food chains, and this platelet ice, this ice crystal matrix, seems to be a critical habitat for those guys to be involved in. And so here we see a mix of silverfish eggs over here, some Hyperiid amphipod over here, and a couple of sea butterflies here. The guy on the left is a predator of the guy on the right, so we keep them opposite sides of the slide. And finally, I just want to kind of do a little shout out to a bit of New Zealand developments. This is some ROV imagery taken by Ben King and his crew from Boxfish. This is a company from Auckland who build an amazing photographic ROV. And just showing these footage here, you can see how an ROV in the water where you wouldn't put a diver, ROV can capture these kind of candid behavioral changes, but also these types of ROV can produce amazing quality video of benthic communities, and it's quite clear how this type of imagery could be just as good for understanding benthic community assembly as you could get from a diver in action. So where is the future taking us? The future taking us is towards more and more robotic exploration. These robots can stay down longer. They don't get tired. They don't shiver, and they can go way deeper than divers can safely go. So this is the technology that's not really the future. It's the technology that's now. It's just that the application is in the future. Okay, my time is up. I just want to thank all of the people I've worked for over time, all the people who provided logistics and funding, and a whole bunch of people whose photographs I have stolen, used, and borrowed, and who have been mentors to me throughout my time working in Antarctica. And that's it.
Thanks so much for your presentation, Ian. What remarkable images and stories that you've got to share with us. I think it's probably a little bit more complicated than sitting on the side of a hole and jumping in, like you said. I think you've probably been a bit humble there. But we've now come to the Q&A section of our webinar. And if you still have questions that you haven't submitted, you can still do so on the Q&A section at the bottom of your Zoom screen. So our first question, and I'll just get it up here, is do divers wear garments that can be heated under the dry suits?
Yeah, no, that's a good question. Answer is some of them do. The heated garments are a relatively new innovation, and the issues are that they're powered by batteries outside the garment, and there's a hole through the suit through which the power is supplied. At the moment, then the only people I've seen using it are some of the American dive teams, and they use a heated vest, which is electrically heated vest, and it does work. We're really desperate for some electric gloves. We can't believe that we can get people on the moon, but we can't come up with a decent pair of electric gloves for a diver to wear in Antarctica. But as of yet, nothing that's sufficiently reliable for us to use.
We've just had actually someone comment and say electric gloves exist. So maybe I'll connect the commenter with you at the end of this year. Another question is about the air. So are all dives using air, or a mixed gases used for deeper work?
So at the moment, all dives are done on air. We have used nitrox a few times, but the problem with nitrox, it really adds a level of complexity which doesn't really help us, because we're not really constrained by dive time or surface time. We're more constrained by cold time. So extra dive time doesn't really help us a lot. For deep diving, then we currently, all of our diving for, I think all of the organizations in Antarctica is no decompression diving. There have been trimix dives done, including using some rebreathers recently as trials. But right now, the conservatism of the diving community and control boards is such that extensive use of mixed gases is not something that we're looking at.
All right, and this sort of moves to the future again. So we've got a question: what's the potential for deploying small manned submarines in Antarctica?
Okay, and again, that has also been done. So there's a private expedition which went down a couple of years ago, which took down some of those kind of 2- and 1-man submersibles. So yeah, there is no constraints on that. The only constraint really is on deployment, making holes, getting them in and out of the water. There was an exceptionally amazing vehicle which was deployed 1 year in Lake Bonny, which was about the size of a Volkswagen, an old Volkswagen Beetle, and it looked quite a lot like one actually, apart from it didn't have any wheels. And that was lowered through a hole in the ice. It was autonomous. It was flown all around the lake, just below the surface of the ice, so it didn't disturb the water column. Yeah, so that technology is completely possible, but the problem there was that they had to make such a huge hole to get a Volkswagen Beetle through, that it took an enormous amount of time and energy and resources to make that hole. But yeah, no, manned submersibles, not a problem, particularly in the ocean where deployment would not be such a big deal. I guess we always think the issues of safety are kind of paramount always in Antarctica. So any time you have that type of technology in action, then national programs will always be absolutely essential that there is some kind of rescue capability available.
Yeah. Okay, and our next question is about climate change. So someone has asked, how are the mammals and fish life being affected by climate change under the ice in the Ross Sea area that you've observed?
Yeah, that's a really good question, and I have to say that that to date there are no real big smoking guns for changes that are occurring, and part of the reason for that is that our understanding of the baseline is still quite rudimentary. And by what I mean by the baseline is that Antarctic systems, like many systems, are inherently, they're inherently stable and they're inherently variable. And so very often communities and organisms will last for a very long time, so they'll respond quite slowly to change. Other parts of the community change very quickly, but they change. But the processes that are causing those changes are difficult to discern at the moment in terms of understanding what's natural variability and what's induced variability. The big things that we're anticipating to relate to change are going to be things like shifts in sea ice cover. And as we start to see more and more of those types of things, that's when we're really anticipating big shifts in the marine system. And that's a critical part of what the Antarctic Science Platform is looking at, those links between sea ice dynamics and the benthic communities, but also, of course, everything depends on sea ice in Antarctica to some extent. And so as sea ice changes, then we will be expecting to see those things. On other parts of Antarctica, on the Antarctic Peninsula, then there have been huge changes in things like penguin populations as sea ice dynamics have changed. So we know these vulnerabilities, and so we are kind of setting ourselves up right now to be able to understand and project into the future.
I think we've got a few people keen to join you. We've just had a couple of people ask, are you taking graduate students?
Yeah, we love graduate students. As I'm sure most folks know, then there is no season this year, so that gives you plenty of time to get in contact. So yeah, just if you're interested, then get in touch and we'll see what is possible.
Just got time for one more question. This is quite a long one. So what is the normal depth range that you work at, and how long would a normal dive be? Also, have you dived close to the Barnes Glacier, and do you do any research inside of the ice caves and glaciers that are underwater in Antarctica? And have you noticed any currents or tides under the ice shelf in the Ross Sea? So there's a few questions in that one.
Okay, I'll try and remember what they all were. So our normal operational limit is around about 30 meters depth. We do dive deeper than that, but we have to kind of be kind of careful when we do that. So dives deeper than 30 meters down to 40 meters we have done, but it's done there's an exception rather than the norm. Typically, our dives would last, and it depends a bit on what you're doing. If you're swimming around a lot, you stay quite warm. If you're lying on if you're not doing very much, if you're doing something that requires you to be still, then you run out of warmth quite more quickly. So typically a dive might be 40 to 45 minutes, an average dive. Dives do get to over an hour at times, and sometimes you're ready to go by half an hour. Now, Georgia, remind me of the next part of the question.
Have you dived close to the Barnes Glacier?
We've dived at Cape Evans, which is from where you can see the Barnes Glacier, but we haven't dived close to the Barnes Glacier. Diving really close to glaciers is something which would need to be done very carefully because of all the usual problems. We have dived on the face of glaciers in the dry valleys, though, so in the dry valley lakes, because those glacier faces are much more stable. And we have done experiments to look at the melting of ice from along the front of the Canada Glacier in Lake Hoare, and in there are some amazing kind of cave-like structures which do form as part of the melting process, and it's a very complicated faces because of these strange kind of heat fluxes that are going on. So we have been into kind of cave-like structures in freshwater glacier interaction sites, but particularly to look at the dynamics of the ice formation and melting on those faces. And there was another part too, wasn't there?
Yeah, final part.
Yeah.
Do you notice any currents or tides under the ice shelf in the Ross Sea?
So under the
sea ice.
Yeah, under the sea ice, yes, you for sure. Current tides, tidal currents, yes. I mean the tide, of course, you can see the effect of the tide on the level of the ice. Level of the ice goes up and down with the tide. Tides are relatively small there though, and there's only one tide a day. But tidal currents and also tidal currents are present. We notice those in some locations. You need to time your diving, and in some areas there are quite strong currents which would potentially cause diving not to be possible. Most diving we do is tethered, so you're on a rope, but you don't really want to be hauling yourself back up the rope because of the current.
Brilliant, thank you so much for that. Well, I certainly could keep asking questions all day, but unfortunately that's all we've got time for. Thank you so much for sharing your wisdom and your discoveries with us today, Ian. It's been a real privilege to listen to your presentation. And thank you to everyone who's joined us today. See you same time, same place this time next week. We'll update the platform website shortly with the recording of this webinar and details of the next webinar. Stay safe, kia kaha.